Calculus, video 18, interesting limits. For my last video on limits, I'd like to talk about some interesting limits, or maybe a better title would be limits of interesting functions. But either way, let's start with this function. F of x is equal to the sine of 1 over x. Now that might not be a function that you're familiar with, but it looks like this, and it's going to help us talk about our next point. The sine of x, the sine of any angle is between -1 and 1. Right? The sine weight exists between -1 and 1. But when we do the sine of 1 over x, it changes things, and you end up with some curve that looks like this. And that's probably not the greatest of all drawings, but you can check out Desmos on your own and type in sine of 1 over x and take a look at this. But what's happening is, as x approaches 0, the sine curve goes faster and faster and faster and faster, up to 1, down to -1, up to 1, down to -1, up to 1, down to -1. We say this is oscillating. You know, picture an oscillating fan, right, going back and forth, to the right, to the left, to the right, to the left, an oscillating fan. This oscillates. But even more importantly, it oscillates between fixed points or fixed values. It always goes up to 1. It always goes down to -1. Faster and faster and faster. And the fun thing on Desmos to do here is once you graph this, to zoom in, and it kind of looks like you're walking down a long hallway. It's kind of interesting. But either way, we say that this oscillates between fixed values. In this case, those fixed values are -1 and 1. What happens to this function if we limit the x's as x goes to 0? Right? What happens as we let x go to 0? And it's just going up, then it's going down, it's going up, it's going down. The answer is it never actually gets to anything. The y value goes up and down forever and never gets to a certain point. So anytime you have this oscillating between fixed values, the limit, as in this case x goes to 0, of the sine of 1 over x is undefined. Undefined or does not exist because it oscillates between fixed values. So it never actually goes to limits to a particular y value. It always goes between several. This is actually also the case if we take a look at the limit as x goes to infinity of just sine x. Right, just your normal sine wave looks something like this. As x goes to infinity, does this curve go to a particular y value? No, it always goes up to +1, it always goes down to -1. It doesn't go towards a particular value. Therefore, and keep going to the left here, therefore this answer also does not exist for the same reason, or undefined, if you will. I'll go undefined since that's how I said it the first time. This is also undefined because it oscillates between fixed values. This works also for cosine of x, and the first example also works for cosine of 1 over x. Same thing, or very similar at least. However, if the curve oscillates, but is what we call damped. In other words, it's oscillating, but it's not going between -1 and 1 each time, but like the values it's going up to and the values it's going down to are getting closer together. We call this damped oscillation. D-A-M-P-E-D, damped oscillation. And that would look like something like this. The limit as x goes to 0 of x times the sine of 1 over x. So here's what this changes. It's taking that sine of 1 over x, going negative 1 to 1, negative 1 to 1, but as x gets close to 0, it's taking a smaller and smaller number times that. The picture, and you could do this on Desmos as well, the picture looks like this. Think about the function here is like the function y equals x. And if I drew y equals x, let me draw it dotted, that would be this. But also draw its negative, like so. So y equals x, this is like y equals x here, this is like y equals negative x. And the curve, that sine of 1 over x, now does the same sort of oscillation, but it peaks here and then minimizes there and peaks and minimizes and peaks, and it goes faster and faster and faster. But as it does so, it's being squished in by the x, because the x is becoming smaller and smaller. You're multiplying that by smaller and smaller values. Same thing's happening over here. It's going peak to trough, but it keeps getting smaller and smaller. Again, yeah, check that out on Desmos and zoom in. That's pretty fun too. In this case, the limit as x goes to 0 is 0, even though it's oscillating, because it's not between fixed values. Those values are squishing closer together. Kind of like a squeeze theorem, a little in a way. Good. We could have another damped oscillation if we have something, just a different function here, like square root of x. Now, square root of x does not exist for x's less than 0, for negative values. So we have to, in this case, do as x goes to 0 from the right, because there's no curve to the left, because you can't plug in negative numbers there, so you can only do this one from the right. But this function, as opposed to having dotted lines here of y equals x and y equals negative x, is going to have dotted lines of y equals square root of x and y equals negative square root of x. It's kind of like whatever that function is, right, out front there, the square root of x or just x, becomes the boundary of the oscillating sine of 1 over x function. Either way, because it's being squished down, the answer here is also 0. All right, next interesting function, the semicircle. And maybe this is less interesting than the last one, but we use semicircles a lot in calculus. And so I wanted another example where we're graphing semicircles, mainly so that you remember them. For when we do other semicircle things. The formula for a semicircle is y equals the square root of r squared minus x squared. R squared minus x squared. This would be the top half of the semicircle of radius r. Or y equals negative square root of r squared minus x squared. That is the bottom half of the semicircle. In this case, we have the positive square root 9 minus x squared. That means the r value must be 3. So the semicircle, top half, because it's a plus out front of here. You don't have to write it, but it's there. Radius 3. Therefore, that's an awful semicircle, but we'll use it. Over here 3, and here negative 3, and top up here 3. And the question is, what is the limit as the function approaches 3 from the left? Well, it's a good thing we're approaching from the left because there's nothing to the right. Coming from the left, we can see that the y value is getting closer and closer to 0. Okay, this same problem, the limit as x approaches 3 from the right of my semicircle would be undefined, or does not exist. I think I've been using does not exist for those. I'm okay with either one. Because there is no curve over here on the right-hand side. Next interesting function, the greatest integer function. Y equals this double bracket with x in the middle. And what the greatest integer function says is, let's say we have the greatest integer function of 3.2. The answer here is 3. It is the greatest integer of a number that is less than or equal to the number that is given. So 3.2. What is the greatest integer that is less than or equal to 3.2? That would be 3. What is the greatest integer that is less than or equal to 4.9? We don't round to 5. We say that 4 is the greatest integer that is less than or equal to 4.9. What if you have like 7? And it is an integer itself. The greatest integer less than or equal to 7 is itself 7. Interesting ones are negatives. Negative 3.5. Actually, let's go negative 3.1. What is the greatest integer that is less than? Be careful here. Less than or equal to negative 3.1. It's not negative 3. It's actually negative 4. Because negative 3 is more than negative 3.1. Watch the negatives there. The picture, the graph of the greatest integer function looks like this. Let's see, here's 0, 1, 2, 3, negative 1, negative 2, negative 3. It looks like this. Everything between 0 and 1 drops back to 0, including 0 itself. But not 1, because the greatest integer less than or equal to 1 is itself 1, and so is everything until you get to 2. The greatest integer less than or equal to 1.5 is 1. Less than or equal to 1.7 is 1. It all backs off to a y value of 1 until you get to 2, and then at 2 it jumps up to 2, and then you have these stair-looking things as the graph of the greatest integer function. Which brings us to things like this. What is the limit as x approaches 2 from the right of the greatest integer function? Well, from the right, here's 2. From the right, we see that the curve, the y value, is approaching 2. But from the left, we see that the y value, as you approach 2 from the left, let's go the color I can see a little bit better here. How about the green? The y value is getting closer to 1. So from the right it's at 2, from the left it's at 1. There's a jump. Therefore, the overall limit, hopefully you're thinking to yourself, the overall limit as x approaches 2 of the greatest integer function does not exist because the left-hand limit does not equal the right-hand limit. Okay, very good. Last one. One more and we'll call it good for this video. We have what's called the sinum function. Sinum function. These are just functions that you'll see kind of throughout calculus, so it's a good idea to introduce them to you now. The sinum function is like y equals, we abbreviate it SGN of x. Sine or sinum of x. And the sinum function looks like this. Y equals the sine, the sinum of x is a piecewise defined function that is -1 for all negative x values of x less than 0. 0, a y value of 0 if x is 0, and a y value of 1 if x is greater than 0. It ends up looking like this. At 0, it's 0. Anything greater than 0 has a y value of 1. Anything less than 0 has a y value of negative 1. This is the sinum function. Which brings us to what is the limit as x approaches 0 from the left? What is the limit as x approaches 0 from the right? And then finally, what is the overall limit to 0? Okay. From the left, as we approach 0 here, from the left, we're coming towards 0, and we see the y value is just staying right there at negative 1. From the right, as we approach 0 from the right, we see the y value is staying right there at positive 1. And that means the overall does not exist. Why does it not exist? Because there's a jump there. The left-hand limit does not equal the right-hand limit.